Okay, I think we must start now. Let me say that it's an absolute pleasure to welcome Dr. Mayukh Panja back to IISER Kolkata for this talk. Dr. Panja completed his PhD at the Max Planck Institute for Solar System Research at Goettingen last year, and is currently a postdoctoral fellow there. For me, his visit is also deeply personal. I first met Mayukh just a few years after I had joined IISER Kolkata, I think almost a decade back, when I went to give a talk at NIT Durgapur organized by the Students' Council there. And I recall that Mayukh came up after my talk. We had a brief interaction, and then later he wanted to do a summer project with me, which he did, and then applied for a position at the SESI MS program. The very first year we actually had the program running. He was offered a position and he joined as a student to the first batch of our MS program. So he was like the guinea pig. And I must say that for students from an engineering background, he had an engineering BTech degree. It must have been quite a challenge to adapt to traditional physics and astrophysics coursework. But Mayukh did admirably well and excelled. And he got himself a position for a PhD at MPI Gottingen. So there, Mayukh did pioneering simulations. In fact, the first simulations of magnetized star spots in stars, other than the star that we know and love very well, which is the sun. And so he's going to be talking about his work on the first ever simulations of star spots today. Mayukh is also a representative of the steering committee of the Max Planck Society Postdoc Net, and he represents chemistry, physics, and technology in the Postdoc Net steering committee. And for those who are interested in pursuing higher studies in Germany at the PhD level or even at the postdoctoral level, Mayukh would be available today from 5:30 to 6:30. I just sent an email to all at IISER. He'll be available at SESI to have a discussion with you, answer your questions, and interact. Let me just end by saying Mayukh is one of the students I have the most fun working with, interacting with, and fighting with. And it's an absolute delight for me to see him doing so well for himself and to have him visit his alma mater. So welcome, Mayukh, and you may now begin your talk.
All right. So thank you, Dibbendu, for that very warm welcome. So I think I should also say that it's a lot of fun. It was a lot of fun working with Dibbendu, and it's a lot of fun coming back. And it's not just likewise for me, it's not just an academic visit, but also a deeply personal visit. And it's really nice, the warm welcome that I received right now. So thank you for the kind words again. And so I'll briefly talk about mostly my PhD work, which, as Dibbendu explained, are the first radiative MHD simulations of spots, and the important bit is magnetized spots, on cool main sequence stars. So what I'll try and do is I'll explain a little bit of the physics of star spots and sunspots, and try and connect them, try and unify the fundamental properties of spots on cool main sequence stars. So here you see a picture of a simulated sunspot. So the title seems like a handful, so I'll try and break it down slowly. I'll first talk a little bit about what is a cool main sequence star and what is a magnetized spot, and then I'll move beyond that and try and explain the physics the best I can. Right, so what is a cool main sequence star? And so this is the HR diagram. So I think a lot of you who have done a course in astrophysics will be familiar with this. So basically, all stars in our universe can be divided into spectral types. And that essentially means that every star has a unique surface temperature and a luminosity. So luminosity tells you how bright a star is, and temperature tells you, well, how hot it is at the surface, right? And so, quick question, can people see my cursor? My mouse pointer?
Yes, I do see it. And if I can see it, everybody else can see it.
All right. Right. So you can see the sun here, right? So this is where the sun is, right? So the sun is a G2V main sequence star. So what do spectral types mean? So the first two letters give you a sense of the temperature. So you can see the temperatures have been classified using letters O to M, and these are the letters are mostly because historical reasons. And within like each letter, you have a subclass of temperature. So for example, G goes from 0 to 9. So G0, G1, G2, G9. And G9 would be the coolest, and G0 would be the hottest. So the sun is a G25 star. And so when you think of, so the cool main sequence stars is, by the way, here. So you can see the main sequence, right? So this is the main sequence where most of the stars of the universe are. And the cool main sequence stars are here. So G, K, and M spectrum. So you can see them here. So these are the cool main sequence stars. So a star can also be, by the way, cool and be a subgiant, for example, right? So these are giants, but they have different luminosities. So why begin with cool main sequence stars? So the reason is very simple is, well, we want to look at stars that are the most similar to the sun. So stars that have outer convective envelopes, very similar surface gravities, and not too different surface temperatures. So we call them solar-like stars. So this is what a cool main sequence star is. And so in my thesis, I focus mainly on G25, K05, and M05. By the way, it's actually V, the Roman letter V, and I keep confusing the two, so I might call them 5 once in a while. So these are the 3 stars that I worked on during my PhD. And so as you can see, so typically luminosity is typically associated with the size of a star. And the size of a star often tells you the surface gravity of the star. So think of it this way. A large star is going to have low surface gravity. A small compact star is going to have high surface gravity. So stars that we have simulated go from G to M. So surface gravity increases and temperature decreases. So you have smaller, compact, denser, cooler stars going from G to M. So these are the stars that I've looked at in my thesis. And so before I go on more about stars, so let's go back to the other part of the title, which is, well, spots. What are spots? So I'm assuming that you know a fair amount of spots because, CESI is primarily a solar physics lab, but I'll reiterate some of the very basic stuff. So a sunspot has basically 2 components, an umbra and a penumbra. And you can see here, right? The umbra is the dark part, the central dark part. It is surrounded by a filamentary structure called the penumbra. And then it's the penumbra is brighter than the umbra, much brighter, but not as bright as the quiet sun. And then you zoom into one penumbral filament, and then you see there's a lot of substructure, right? And then you zoom in on, and this is a Nature paper cut out from a Nature paper on your extreme right, and it shows one penumbral filament. So this is from 2002, and you see that there are these bright structures, and there's a thin dark core running through the middle of the penumbral filament. And so the point of me showing you this slide is to show, well, that sunspots have a lot of substructures. They're not bland, objects. And the other point that I want to drive home is that we know a lot about them. If you can, probably it's not very clear, but these thin dark cores have a resolution of only 100 kilometers. So it gives you a sense of, how much detail we know about sunspots. And so this is the morphology of a sunspot. Now let's look a little bit at the physical properties of a sunspot. So what is a sunspot? A sunspot is essentially, well, it is a place of very strong magnetic fields. So you have plots of 4 quantities here: temperature, magnetic field strength, inclination, and your line of sight velocity. And so as you can see, the umbra is dark and cool, which is surrounded by a brighter, somewhat hotter penumbra surrounded by the quiet sun. And you have the strongest magnetic fields in the umbra, surrounded by weaker magnetic fields in the penumbra. And the strong magnetic fields in the umbra are also vertical. And as you can see in the umbra, your line of sight velocities map suggests that the flows are quenched, which means, so if you see, they're roughly around 0 kilometer per second, which means the convection is that the flows are not coming up. So what is going on here? So basically, the basic physics is that when you have strong vertical magnetic fields, they prevent overturning convective motion. So what does that mean? So when you have strong vertical magnetic fields, the flows are magnetized, right? And therefore, they are guided by the field lines, and therefore they cannot do their 3D motion. And so you cannot have granulation. And so the energy that would have otherwise come up fails to come up, and it reduces the temperature. So you have basically vertical magnetic fields. Strong vertical magnetic fields in the umbra create a region which has low temperature because, again, it hinders the transport of energy, and that is sort of reflected in the line of sight velocity. And so this is the very basic physics of a sunspot. And then when you zoom in into one penumbral filament, so this is, let's say, the average penumbral filament, and on your left you have the umbral side, on your right you have the white sun side. So you have a upflow towards the umbral side, and then the flow moves along the length of the penumbra. This is the line of sight, and so this is a sunspot at the disk center. So the line of sight would not give you the horizontal flow, but believe me that is the case. So you have flows coming up from one end, and they flow along the length of the penumbral filament, and on the other side they go back into the sun. So this is, well, so it tells you, we understand a fair amount of physics about sunspots. We know what they look like to a large extent. We at least understand very well what the basic physics is. We also understand, so it's not very apparent from here, but we also understand why do we have these thin dark cores and all of that, thanks to very detailed observations, and which have been complemented by radiative MHD simulations. So I'm not going into the details, but I want to show you that we know a lot about sunspots. And I gave you a brief overview of the physics. So the next question is, well, how much do we know about spots on the sun? Or let's generalize the question a little bit more. How much do we know about other stars at all? So we know a lot about the sun, right? So I want to show you this plot here. So focus on the left. So these are stars. Okay, let's ignore the title star spot observations. These are observations of the full disk of a star. It's the same star, but using three completely different techniques. So on the top, you have interferometry, you have Doppler imaging, and you have light curve inversion. Again, let's not bother with what they are, but they're three independent techniques. And you can see that they are wildly different, right? So look at, again, it's the same star, and you can see that they just give you wildly different results. And you can see how much we know about other stars. So, asking a very fundamental question like, okay, what does another star look like? Well, we don't have an answer. We have, at best, some very uncertain information about the large scale structure. So as you can see, we are nowhere near, first of all, we are nowhere near even conclusively answering the question, well, are there spots on other stars, right? That's also very important. It will be very surprising if they don't. But the point is, we cannot conclusively say with 100% certainty that they do, right? So you can see the state of observations on other stars, but we do have techniques that let us allow, probe, maybe not the spatial structure, but may they help us glean some information about spots on other stars, using spectral lines. For example, a very good technique that is useful for measuring star spot temperatures are molecules. So what happens is molecules dissociate when the temperature is above a certain range, and they can only form in the cooler parts of a star. So the presence of molecules in stellar spectra typically signifies that there is something cool that allows the formation of molecules. So this is one example of how you can indirectly probe the temperature of star spots. And then we have this plot here. This is a very famous plot in the stellar physics community, at least. So it basically says on the y-axis you have T photosphere minus T spot, and on the x-axis you have T photosphere. And you see a very clear trend. You see that the hotter the star, the higher the temperature contrast. And so the reason for it was not very clear. And so, for example, one theory that people proposed was, we are measuring the temperature of the full spot, and maybe on cooler stars, the spots have larger penumbra, which bring down the temperature contrast. So this was one of the theories that was floated, and we didn't really know what the answer was. And so let me explain a little bit of the plot is. So all the squares that you see are subgiants and giants. All the circles that you see are main sequence stars. And you find another interesting thing is that this trend is, well, it doesn't matter. The size of the star doesn't matter. It seems to apply for all stars. And you see some of these points are connected by these straight lines. And so these are observations of the same star. So you see that even for the same star, you often get very different results, which is apparent from the plot that you saw on the left. And on the lower half, you have magnetic field strength measured on the stellar surface. And this is a very important distinction. These are not magnetic field strengths of individual spots, but of the stellar surface. You cannot measure magnetic field of an individual spot because spots are too dark, which means that their contribution to spectral lines is very little. So typically, you use Stokes inversions for measuring magnetic fields. So you look at the Stokes V. So maybe, some of you, I guess some of you might be familiar with it, but the basic point is that the signal of your Stokes V is so weak because the spots don't contribute a lot to the overall stellar brightness because they're dark. It's very, very difficult to measure the field strength of an individual star spot. So basically, this is all you have. The average field strength on stars of different surface temperatures. So this is basically the state of observation. So I guess now it is quite apparent. Well, why do you need simulations? So let's ask some very fundamental questions. So what do spots on stars other than the sun look like? How bright are they? How strong are their magnitudes? So these are very basic questions, right? And what is the physical explanation? So like I said, there was some speculation in the stellar physics community about, why do we see this trend here? So can we explain this physical trend? And so while I was working on problem 1 and 2, I found out, apparently that the initial condition, or not, let's say not the initial, the subsurface structure of spots. So I use certain, let's say, flux tubes. I'll explain what a flux tube is a little bit later to produce my spots. And they affect the surface appearance. And then that actually led to a separate independent study of how the subsurface structure of a spot helps shape the appearance on the surface, and whether looking at the surface of a spot, whether can we tell something about what is going on underneath. So that was a question that sort of originated organically from my star spot thesis. That was not part of the plan, and that just happened along the way. And that we wrote a small abj letter paper for problem 1, problem 3, and problem 1 and 2 was my main PhD work. So we use the Murrum code. So what is the Murrum code? So the Murrum code, which stands for Max Planck University of Chicago Radiative MHD Code. It solves the equations of compressible MHD and the radiative transfer equation in a box in a star configuration. So again, it's a mouthful, and then let's go slowly through it, and I'll try and explain what this means. So on your right, you see this whole ring-like structure, right? So imagine this is the whole star, your circle, and on the top, you have this little box. So that is all that we are simulating, right? So we call this box in a star. So there are other simulations which are called star in a box. What they do is they take a 3D box and they put the whole star. And there are groups like the Pencil Code, and you might have heard of them. That's the stuff that they do. We have a different approach that is box in a star, and apologies. So what we do is we ignore the global dynamics completely, but what we focus on is the surface dynamics, and we get them extremely accurate. So let's look at this picture here. So this is actually a composite image of a sunspot. So half of it is a simulated spot, and the right half is an observation. And as you can see, the simulations are doing exceedingly well. And in fact, I would say that the simulations are actually doing better than the observations because they have just so much more detail. And maybe, with the advent of these new telescopes like DKIS, maybe the observers can catch up with the level of detail that we get with our sunspot simulations. So as you can see, that the level of realism that we achieve using the Murrum. So as you can see, that the premise is quite clear. And we have amazing observations of sunspots. We have this code which does a pretty good job of not just reproducing the surface the way it looks, but this was also used to understand a lot of the microphysics, of sunspots. So we have both these things, and so let us expand this knowledge and try and use the code to answer the questions about star spots. And so the Murrum code has also been used to simulate magnetic regions on different kinds of spectral types, and this is the work done by a previous student before me who basically looked at large regions on different spectral types, and my work was to improve upon what he did and expand the study to spots on different stars. And right. So what do we do with the Muram? So these are the MHD equations basically. So on the first you have the continuity equation, which basically tells us that mass is conserved, right? And next we have the momentum equation. So the momentum equation, for those of you who are new, you can think of it as a sort of Newton's law of motion, right? On the right hand side you have mass into acceleration. Well, it doesn't look like it, but if you use your imagination a little bit, you can see that this should look like mass into acceleration. On the right hand side we have the forces. So you have pressure difference. This is a Lorentz force, which is the magnetic force acting on the fluid, and this is gravity. And then you have the energy equation. So think of the energy equation as how much work does a force do? And if you remember a little bit of high school physics, you will remember that work equal to force into distance and power equal to force into velocity. So just recall a little bit of high school physics, and you can see the terms are sort of like that. Like look at, for example, this rho g term, and this is dE dt, right? So energy per time, and then you can see force into velocity, right? So you will obtain. So if you take the equation, the momentum equation, and then from there calculate the energy equation, you will get all the terms except q rad. So what is q rad? Q rad is what couples the MHD equations with the radiative transfer. So q rad is a radiative cooling or heating, and that is modeled separately. So I'll go into that a little bit, just one slide after. And then you have the induction equation. So all of you must be, this is your bread and butter, the induction equation. So you know exactly what it is. And one thing you might notice is that there is no diffusion term, right? So also in the momentum equation, you see that there is no viscous term, right? So these are the ideal MHD equations. We do not add any artificial viscosity or artificial diffusivity. We have something called hyperdiffusivity, which is, if anywhere there are very sharp gradients, the code takes care of it. And finally, you have the equation of state. So the equation of state is what, so the equation of state is what you need to close a system of equations. So if you have more number of equations than the number of variables, if you have more variables than the number of equations, you need one more equation to close your system of equations. And this equation of state basically relates to thermodynamics. So if you put in internal energy and density, it gives you back temperature or pressure. So based on these two things, so for either from temperature and pressure, you can go to internal energy and density, or the other way back. And I made a point of saying that the MHD equations are coupled with the radiative transfer in the q rad. So we have a whole radiative transfer routine, which was basically a person's entire PhD just making the radiative transfer work. So what we do is we solve the radiative transfer equation. So what does this mean? So this means that di d tau, so it's equal to S mu minus I. So basically it tells that, let's say you have a blob of gas. So any radiation passing through it, so let's say there is radiation coming through one end of this blob of gas and coming out of the other end. And so if the blob of gas is a certain temperature, it will emit at the temperature. And because it has some inherent opacity, it will absorb some of the light, right? So the absorption part is given by the second term, and the emission part is given by the first term. So we solve this equation, and then so we solve this equation by actually shooting rays. We have 8 directions, and we shoot rays in 8 directions. And then in the end, we sum over all the solid angles, and then what we get is the radiative flux. This gives us the radiative flux, and then this is the radiative heating or cooling. So all of this is done. We shoot rays in 8 directions, and again the rays are shot. So again we assume that the source function of these rays is based on the temperature, and the opacity is based on the temperature and the pressure. So based on this, the radiative transfer equation is solved. From there on, the radiative flux, and then that gives us the radiative heating or cooling, which is fed into the energy equation, right? So this is the basic setup of the Muram. And so I have 20 minutes time, good. So I'll dive now straight in the results. So this is basically the background, right? So this is how we simulate a spot. So our box kind of looks, so look at the left-hand side, that is our initial condition. The box sort of looks like this. So on the surface, you can see granulation, right? It's 10.3 megameters deep, 6 megameters across, and 36 megameters long. And this is the initial condition of the magnetic field. So this is what is plotted here is BZ or B vertical. So as you can see, it is very strong near the base, and then as we go up, it fans out. It fans out because some of you might know the reason. Del dot B is 0, which means the flux at every surface has to be the same, because magnetic field lines cannot start and stop randomly, and then it fans out as we go up. So this is our initial condition. We let it run for a while, and we let it run until it had reached quote unquote statistical equilibrium, which sort of means your basic things are not changing. So as you can see, this is after it has been run for a while. So the magnetic field is not just concentrated in the flux tube, but it has it has formed pores. You can see an formation of an umbra, and if you look carefully, you can actually see that the surface is undulating. So the surface of the umbra is a little deeper than the surface of the penumbra. So this is called the Wilson depression. So when we see that a spot has formed, so we stop our simulations and we analyze the physics. And this example here is for the sun, and we repeat this for other spectral types. Right. So these were basically the simulated spots on each of the spectral types. On the top you have the G star, the K star, and the M star. And so to begin with, so there are a few things that you should notice here. So one is, so look at the X and the Y axis. So the simulations were conducted in a way that the granule size, the size of the granules, not the size of the granules, sorry, the number of granules are same for all the spectral types. So more or less, each simulation box of each spectral type have the same number of granules, but as you can see, their physical lengths are not the same. And this is a well-studied result. There were simulations done of different spectral types back in the 1990s by Nordlund and Davis. This is not something new, but it highlights just. So as you can see, the sun, this is 36 megameters, this is 27, and this is 10 megameters. And as you can see, the granule size, a solar granule is roughly 1 megameter to 2 megameters wide, whereas for the M star, that is probably a couple of 100 kilometers, right? So this is the first obvious difference that you would notice. And this is basically, granule size is a function of the local pressure scale height, which in turn is a function of the surface gravity and temperature. Now, you could quickly derive the formula for pressure scale height, and you can see that how it determines it's dependent on the surface gravity and temperature. And then you could see that it scales something like P by G. So higher the temperature, larger the granule size, higher the gravity, smaller the granule size. So that is one thing you can do. But think of it physically. When you're going from the G star to the M star, you're going to a colder, denser, more compact star. And that is sort of reflected in the group. So think of it as everything being, squished down to smaller length scales. It's a little, maybe that would help you with the physical intuition, right? So you have some hot and bubbling and large, and then you take that atmosphere and you squish it down to something that's denser, compact, and cold. And that is why you have such a difference in granule size. But that is not our main result. That was found in the 1990s. And the most important result is, well, hotter the star, higher the spot contrast. And that is in tune with what the observations show. And this is the biggest results of my PhD. It confirms, that those observations, despite their limitations, are actually correct. And this is very good news for, all those people who have been making those observations. So take a look at the contrast here. So the color bar shows, the intensity in units of, well, this 10 to the power 10 erg per centimeter square per second per steradian. Apologies. So if you look at the contrast between the umbra and the white star, you see a pattern, right? For example, the solar umbra is the darkest in comparison to the solar white star, whereas the M star umbra is the brightest in comparison to the M star white sun. So for example, if you see here, for example, look at the M star, for example, the average value of its white star is around 0.4, and the average umbral brightness is 0.3, so roughly around 75%. So M star umbra is 75%, almost 70% bright as its quiet star. So that's not very dark. And for the G star, your umbra is only 20% as bright as its quiet star. So this was very interesting. And so what I'll do in the rest of my talk is try and explain a little bit of the physics. And if you can get the physics of it, I guess I'll consider my talk successful. And the third point is that all the spots show penumbral filament formation. That is not a part that I focused on my PhD a lot. That is something that I'm actually working on now by doing, large spots. So these are, as you can see, spots that are square in shape. These are great for understanding the physics, but the look and feel of it is, as you can see, it's not as cool. And so what I'm doing now is exclusively studying the penumbral filament formation, but the basic physics, why do hotter stars have higher spot contrast? That was the work of my PhD. So again, I'll give you a brief, explanation of the basic properties. So I see I have 15 more minutes. So, so look at the temperature. So whatever you see in the intensity is reflected in the temperature. So the average, the temperature in the umbra goes as low as 4,200 Kelvin, and the quiet star is around 6,000 Kelvin, and some places it goes even higher. And so the temperature contrast is around 1,800 Kelvin. And for the M star, the temperature difference is much, much lower at 400 to 500 Kelvin. Ignore the middle plot for now. On the right, you have the magnetic field strength. And the magnetic field strength for the average magnetic field strength for the sunspot umbra is 3.4 kilogauss. The K star is 3.2 kilogauss, and the M star is 4.3 kilogauss. So they're roughly in the same range. The M star has the strongest magnetic field strengths, and the K star and the G star have very similar field strengths. In the middle, you have something called a Wilson depression. So many of you might not be familiar with what a Wilson depression is. So Wilson depression is basically, it tells you how far you're looking into the surface of a star when you're looking right above a spot. So what happens above a spot is, one, it's lower, its temperature is lower, and opacity is a function of temperature, which I'll talk about later. So opacity is a function of temperature, and also the magnetic field strength, the magnetic fields remove some of the gas and create a sort of a local vacuum, which means your gas becomes rarer locally above a spot because it's rarer, and your opacity has also decreased because of the decrease in temperature, and you can see deeper into the surface. So the question is, how deep can you see into each spectral type? And so you have G, K, and M here. So as you can see that, in the G star, you can look the deepest, it's 600 kilometers. And for the M star, you can look only 50 kilometers deep. So you can see a 10 times difference. So a lot of the difference is because of the pressure scale height. So again, the pressure scale height not only determines the granule size, but it also determines the Wilson depression. But also when you express the Wilson depression in terms of the local pressure scale height, it turns out the G star has a much higher Wilson depression than the M star. And I want you to sort of keep this in mind, because I'll come back to this Wilson depression later, and this will play an important role. So again, quickly I'll go over how it compares with the observations. So the blue line, the green line is what the plot that I showed you in the very beginning, and the circles, the other stuff is from my simulations. The blue points are if you calculate the temperature difference at the photosphere, and the red points are if you calculate the temperature difference a little bit above the photosphere. And so why a little bit above the photosphere? Because sometimes you use spectral lines to basically retrieve temperature information, and the spectral lines do not necessarily form at the photosphere, but a little bit higher. So which is why we put in these red spots as points as well. The important thing is that the trends match. The exact values, well, they're also very close, which is great. I'm sorry for the drilling noise behind me. But the important thing is that the trends match. And in the lower half, you have basically the field strengths obtained from our umbra. And again, the dashed lines are fit to the points that I showed before. And again, remember that those were not spot magnetic field strengths, but field strengths of the whole star. But regardless, what you see is that what we obtain is within the range of what has been measured so far. Right. So what determines spot temperature contrast? So let me try and explain the physics a little bit. So I'm sorry about the noise. So the temperature contrast is determined by something called the H minus opacity. So what does it mean? So if some of you have done the introduction to astrophysics course, you will see there's a chapter where they dedicate a section on H minus opacity actually. So some of you might know the concept. I'll explain it a little bit here. So what happens near the surface of a star, of a cool main sequence star, is there are loose electrons that attach themselves to hydrogen, and so you have these H minus ions. And so what happens is that there are photons, and these photons knock out these free electrons, and basically these photons are absorbed, and that is what creates opacity, right? So what is opacity? Opacity is basically how much of your light is, it's a measure of how much of your radiation is absorbed, right? And so as you can see, that if the temperature were to be too hot, then the H minus wouldn't be able to exist because the electrons would be dissociated anyway. They wouldn't be able to latch them onto the hydrogen, because if it's too hot, just like molecules dissociate, it would be dissociated anyway. So in cool main sequence stars, where you have this temperature conditions that free electrons can attach themselves to hydrogen atoms, your opacity is dominated by the presence of the abundance of H minus basically. And so again, to reiterate, your photons that come in, they knock off these free electrons. The photons are absorbed, the electrons are let go, and this is what creates opacity. And the dependence, so H minus has and this has been well studied, H minus opacity has this very strong dependence on temperature. I think it's T to the power 9. And so the higher the temperature, especially in the 3000 to 6000 Kelvin, this is where it operates. And the closer you're to the 6000 Kelvin mark, the sharper your opacity increases. And so again, so it depends, it has a sharp dependence on temperature because of a multitude of reasons. And I'll not go into the reasons in much depth. So let me just say this, for example, it depends also on the availability of free electrons, right? So if you have the presence of other metals, it should be hot enough that you have the availability of free electrons, but again, not so hot that they cannot attach themselves. And you also, the opacity depends on, again, the energy of the photons coming in, which again depends on the temperature. So it depends on a multitude of factors. It's a complex process. The main point is that H minus opacity, which is the main source of opacity for cool stars, the surface, has a strong temperature dependence, and it sort of hits a peak at 8000 Kelvin. And so what happens at 8000 Kelvin is your H minus opacity reaches a peak. And look at where this temperature is for the G star and for the much cooler M star. For the much cooler M star, this happens much deeper. So let me explain this plot again. So this is a vertical cut of the temperature. So you have these weekly lines of the pressure scale heights. So 0 is the surface, -1 is 1 pressure scale height above, -2 is 2 pressure scale height above. So again, pressure scale height is the height after which your pressure drops by a factor of E. So that is how we basically think of depth on a star, because physical distances make very little sense. So 2 is 2 pressure scale heights deep, -2 is 2 pressure scale height above. If you look at the temperature stratification, again, so by the way, the middle is the spot, the rest is outside. If you look at the temperature stratification, 8000 Kelvin is very, very close to the surface here. In fact, I think it's right below the surface for the G star. And for the M star, this is happening much below. And as a result of that, what happens is the opacity increases very sharply for a G star. So it goes from less opaque to very opaque very fast. And let's look at that a little bit more. So what does it mean? So here I've actually plotted something that would give you the idea a little bit more. So this is the percentage of energy that is being transported via radiative energy transport. So again, this is the same plot. But this, so again, in the middle, so the spot, whatever is within the spot has been demarcated. So this is a vertical cut, remember. Whatever is within the spot is within these red lines. So you have 0, again, is the surface. -1 and -2, again, 2 pressure scale heights above. 2 will be 2 pressure scale heights deep. And so the colors show what percentage of the energy is transported by radiation, and the rest will be convection. So roughly you can think of it this way. So yellow would be radiation, blue would be convection. So wherever you see this deep shade of blue, the energy is transported exclusively by convection. And wherever it's exactly yellow, the energy is transported exclusively by radiation. And so what a very interesting thing happens for the sun is that the change from convective energy transport to radiative energy transport happens very fast. Look here, for example. This happens, over a span of just half a pressure scale height. So you have a lot of the energy being transported by convection, and then near the surface, it gradually transforms to radiative energy transport. If you look at the M star, this spans out over 2 pressure scale heights. So what that means is something very interesting is happening. Even below the quote unquote surface, a part of the energy is being transported up by radiative processes. And this is basically what determines spot temperature of contrast. So why is a spot cool? Why is a spot dark? A spot is dark because it prevents the transport of energy, right? So you have these convective motions. On the sun, you have convective motions. You put in strong magnetic fields. The convection is stopped. It completely messes up the energy transport, and you have a dark spot. For an M star, the magnetic fields are less coupled with the energy transport. So this is really the main take home point. The magnetic fields are less coupled to the energy transport processes simply because your magnetic fields do not mess with the radiation. They change the convective transport, sure they do, but again, as you can see for the M star, the convective energy transport is less important. Sure, it transports a lot of the energy, but radiative processes begin to play a non-trivial role even below the surface. And this figuring of the physics was really the main result of my PhD. So this is what determines spot temperature contrast. The other question was, well, what determines umbral field strength? And so we found something very interesting. So again, like I said, so Wilson depression is really how deep you're looking into the star. And by now, I guess you can imagine that the Wilson depression again is very strongly coupled to the opacity, right? Because how deep you're looking into the star depends on the opacity. It depends on the density. And so again, you can see that how closely they're connected, right? So, and also an M star is much denser than a G star. So what is going on here is basically for an M star. So again, so let's go back, take a step back, and let's say you naively try and imagine what would be the magnetic field strength for a spot on an M star versus a K star versus a G star. The naivest thing that you could do is simply write B squared by 8 pi equal to P, as in your magnetic pressure equal to pressure outside. And on an M star, like I was explaining before, it's cooler, compact, denser. It would be much, much stronger, the magnetic field strength, because your pressure is much higher. But we see that not to be the case because the field strength you're measuring is not that high because you're not looking that deep into the surface. And again, you're not looking in that deep because again, the gas is not that rare in an M star. And again, the opacity doesn't depend sharply on the temperature. So I think I'll end my talk here. I think I've spoken for 45 minutes and I think this is enough physics for one day. So what I did essentially for my PhD was do the first radiative MHD simulations on spots and other stars. We now have an idea of what they might look like. We have theoretical estimates of star spot contrasts and magnetic field strengths, and I think this is important because it places constraints on the inversions that observers use to retrieve star spot properties. And the best part for me, the most satisfying part for me, was the physical insight that we got into the processes that govern the surface properties of star spots. And before I end, I'll talk a little bit, I'll spend a minute talking about what I'm doing now. So I'm basically expanding on this work. So during my PhD, I focused a lot on cool main sequence stars. So now I've moved on to doing subgiant simulations, and they have their own. So these are giant stars, much larger than the sun, with much lower surface gravity. And that means, as you know by now, lower surface gravity would mean higher large pressure scale heights. So they have massive granules and very large Wilson depressions. I'm basically looking at what happens to, for example, the surface dynamo, the local surface dynamo, the Plage regions, the magnetic fields, and maybe also in the future I'll look at spots. I'm also, so these things have applications in, for example, detection of exoplanets, right? Because what essentially people do is when they detect an exoplanet, they look at dips in the light curve, right? When you have a planet crossing a star, you would have a lowering of the amount of light that you receive from the star. And that is exactly what would happen when a spot would move across the surface of the star. So there are some applications there. So basically, since then, I've been expanding this work and, trying and see how I can, connect basically what we know about the sun to larger, stellar physics. So thank you, and let me know if you have any questions.
Thank you, Mayukh, for this exciting work highlighting this exciting work that you have been doing with your group at Max Planck. Let me add that what Mayukh has achieved is something that we hoped for as an ideal sort of scenario when he started the MS in Space Physics program at SESI, where we expected people from engineering background would come in, gain physical insight, and apply their skills that they pick up in computation as well as instrumentation during an engineering program. And with this new knowledge of physics, provide new insights in the domain of space sciences. Mayukh is a shining example of that, and more recently, perhaps not everybody knows about this, Athira BS, also a student of our first MS batch, who actually continued to do her PhD here, has won the best thesis award from the Indian Laser Association, which is really a proud moment for us, because this prize recognizes a thesis coming out of India, and somebody from an engineering background, having worked in the interface of astronomy and space optics with physicists and astronomers together, is getting this recognition. So I'm glad that this happened when Mayukh is actually already here, and just wanted to mention this. Mayukh would be also happy to know about this. Athira is not here today with us, but I just wanted to kind of talk about that. Okay, so now
that is excellent news. That is excellent news. I think that is very well deserved. She's a hard worker.
We're very proud of this, particularly because Athira had a big challenge really adjusting to a more physically grounded coursework. I'm just so proud of what our students have been doing. Anyway, so now the talk, I have several questions, but I'll hold my guns, and the talk is open for questions by everybody.
So hi, Mike, this is Soumya. So I have a question regarding the observations of magnetic fields on other stars.
Go ahead.
So when you say that the
There's
strokes
a lot of background noise. Can others who are not speaking just mute your microphone, except Mayukh, of course?
Yeah, I think we are okay now. Yeah. So when these observations happen, the inversions are important for gaining the insight of the magnitude of the magnitude. We need the V component to be measured correctly, to be inverted correctly. The AQV, and the V is important for the magnitude.
I'm really sorry, but can someone? I did not understand what the gist of it was.
Shlomo, you're completely breaking up. I don't even recognize the voice that's asking the question.
Oh, okay. I'll just change.
Hello. So am I audible now?
Yes. Much better.
Okay. Thanks. Okay. So my question was, in the observations of IQUV components, you mentioned that V component is important for inferring the magnetic field strength.
Line of sight, yes.
Line of sight magnetic field strength.
Yes.
Okay. So the observations for other stars is already available for these inversion codes, or is it's still going on or something? I mean, what is the kind of accuracy that they have achieved until now?
I mean, like I said, so you have magnetic field maps. So these are temperature maps. You have magnetic field maps as well for other stars. So this is Doppler imaging. So you have this Doppler imaging technique can also be applied to Stokes V, right? And so you also have similar magnetic maps, but of course they do not have they do not have the same resolution even as close to the sun naturally as you can expect. And what a lot of people suspect is, like I said, right? So you have the map of the full star, and what people think is that these Stokes-V maps actually represent the large region magnetic fields and not so much the spot, because the large regions are brighter and they will contribute more to the Stokes-V. And what you're essentially seeing is a facula map of the other star. That is something that people, but these things are being done, yes. They're available, they're being done, there are papers on it,
Okay.
but they're not spot magnetic field strengths.
Okay. So, but we know that the magnetic activity is high on those kind of stars.
What does it mean? What kind of stars?
I mean, where the observations are there, and we say that these are for plages, not for exact spots.
What do you mean by the activity is higher for what kind of stars?
Like in sun, we see number of sunspots, higher number of sunspots during a sunspot solar activity maximum period, right? And when we observe for the other stars, do we know that it's going on? It's going through a maximum phase where we expect to see some spots or not?
What I am not sure I understand your question.
So what I'm asking is, and so when we observe something and we are categorizing them as plages, and we expect that those plages are not actually plages, they can be spots, and due to our observational constraints, we are not able to resolve those kind of magnetic field strength for a different star spot, right? I mean,
So there.
I'm not sure that I also understand the question that Shom is asking, but I think what he's trying to say is that do we have enough observational resolution or understanding to distinguish between spots and plages in distant stars? Is that what you're asking?
Yeah.
Okay. Yeah. So from not so much from the so again, this is a theory. This is what people will tell you when they look at the Stokes-V maps, that it's possible that it could be more representative of the plages. Again, by the way, I'm not an observer, but I'm just okay. So this is what people say. But again, so the important thing is that so there are many ways you can probe the surface of a star, right? It's not just magnetic field strength, but also temperature. So the way we know that, so for certainty, well, nobody has seen a direct observation of a star spot, but I would strongly argue that star spots exist because, again, the most important thing is presence of molecular lines. If you have a hot star and you get the presence of molecules, it can mean only one thing, right? It means that there must be patches of cool regions on that hot star that allows the formation of those molecules. And I think that is the strongest argument that you can have for the existence of star spots.
Yeah. Okay. Thanks a lot. Nice talk, by the way.
Mm-hmm.
Hi, Mayukh. This is Chitradeep. Am I audible?
Yeah.
That was a nice talk. So I have a question, particularly from the modeling point of view.
Yes.
You mentioned that you use this hyperdiffusivity instead of non-ideal induction equation. Can you please elaborate how does that help specifically in this context of star spot modeling?
Well, that's not the idea. The question is not how does that help. The question is, so the moment first of all, it's not just done for star spot. That is a Muram policy that we just do not have diffusivity, or we chose our code to be that way. And at the end of the day, this is a choice, right? You could, in theory, write a code that has diffusivity in it, right? But the reason we chose to not have diffusivity because it introduces a free parameter, right? So it means the moment you have, let's say, magnetic diffusivity, you need a diffusivity coefficient. And what do you do with that, right? That raises a whole bunch of questions, right? Similarly, again, for viscosity, right? And we just decided it was a decision that that's not what we're going to do. And number one, the second thing is that a diffusive code it makes it less realistic. Let me explain what it means. If you look at a Muram simulation, for example, look at this. You see a lot of substructure. So you have to understand what creates that substructure, right? Why do you get to the corrugated features that you see? What creates the substructure is how much you can resolve the turbulence. To what extent you can not. The more diffusive your code will be, the more the structure will be washed out. I hope that is physically sort of pure.
Yes, yes, yes.
Right?
That's
So
true. Yes.
if you put in explicit diffusivity, your structure will be washed out. I mean, we don't want that.
But Mayukh, you have convection, right?
Yeah, we do.
Right. So I mean, this is why I often say that modeling is really at the interface of art and science. And one needs to be really intelligent if you want to set up a good model. And you need to worry about what is important, what is not. So here in this kind of simulations, there are multiple things. One, you are looking at a really like a strong field regime where you are simulating a start spot or a sunspot. And therefore, it is expected that the magnetic field will dominate over the plasma dynamics. So you expect that to some extent, the typical turbulent diffusivity that you expect in plasmas will be to a large extent suppressed or quenched by the strong magnetic field. Second, turbulent diffusivity really is a parameterization of turbulent convection that occurs in atmospheres of stars, right? In many ways, at least
Depends on the length scales you're talking about.
Correct. Also, but here, I mean, you have convection because you're putting in a density stratification, you're putting in a thermal flux, temperature gradients, and you have explicit thermal convection, and that also mimics the physical transport that is achieved by having a diffusive system to a large extent as well, right? So you can get away by not considering it and not loading or making your code much more complex than it needs to be, because you're already capturing the physics that needs to be captured.
Yeah, exactly. Yes. So any diffusive, so for example, a lot of things are modeled as diffusion, right? For example, think of a surface flux transport code. The diffusion there is not the same as the diffusion in Muram, because the diffusion there, so when you're looking at the breaking up of an active region in a surface flux transport code, you're deciding to model that breakup using a diffusive term. Now, if you have convection that is automatically breaking up your spot, there's no need to do that because, well, so as they've been said, a lot of it is a matter of choice at the end of the day. And I think it's important to know that. And I'm sure you can add in a diffusive term in it, and there are lots of codes that actually have explicit diffusive terms. But again, like I said, in our group, that we believe that is just bringing in a whole range of another set of questions that you don't want to have.
Okay, got it. Thank you.
Okay, maybe I can ask a few questions. So I had this thing. What was that about? Yeah, you said something about 8 rays. You're integrating in the radiative module, radiative MHD model, in the radiation model particularly. You're shooting off 8 rays, and you're solving the radiative transfer equation along those 8 rays, and then feeding back into the MHD.
Exactly.
Now, so what is so sacrosanct about the 8 rays? Is it something that is the minimum number necessary to resolve the radiation of radiative physics?
So I think there is nothing sacrosanct about it. I think the more rays you have, better, right?
Better it is. Yeah, that's what I was wondering. But why 8 and why not 6?
Yeah, exactly. So I think what people did is that. So the thing is, you settle for the number of rays that you're happy with. I think that's the best answer, right?
Okay.
I mean, you could do 24. As in,
rather, can I mean, is it possible that it stops making a difference if you go from 8 rays to 6?
Exactly.
The results converge. Is that what is going on here? Maybe, perhaps. That I would do. For example.
Exactly. So that, and also more the case of, well, at some point. So actually, the radiative transfer bit is the most computationally time-taking part of the entire code.
Correct.
And so the question is, well, yeah, sure, you could do 24 rays, you could do 36 rays, but at just some point, the question is, so again, it's a matter of choice, right? The question is, so the balance of how many rays give you a good enough result that you're happy with. Right. And yeah, for us, it's 8. Some people have done 6. I think there are people who have done 12, but I think they're in the same range. And these are also very traditional and historical in the sense that, so I really, I am in awe of this paper by Nordlund and Dravins, and I think all of you should read this paper. And the reason I say that is because his first radiative MHD simulation was in 1986. So think of that. And I find that really amazing. And a lot of the stuff we do till today has been motivated by the stuff that was done in the 1990s. And that I think is, very, very, inspiring that back in the 1990s, the level of computers that you had. A lot of the stuff, actually, even the radiative transfer, a lot of it is actually motivated by that.
Okay. Okay, so the other, so what, I'm just trying to recall what else they have in mind. Oh yeah, so does the magnetic field dynamics feed back into the radiative module here, maybe perhaps through dissipation? Is that really important in the photosphere where you have plasma beta close to 1, maybe even higher?
So this is the
Or
thing.
is it something you just not worry about?
So this is the thing. So there is an explicit connection. So the radiative transfer equation doesn't have magnetic field, right? It's as simple as that. But that doesn't mean that they're not connected. So for example,
you're feeding that back into a magnetic module, but so now in a system where you have reconnection like the solar atmosphere and heating, that would now feed back into the radiative module, of course, right? And this is why this radiative MHD codes are just so complex and the subject is so difficult, right?
yeah.
Because you're solving for the radiative transfer, but that depends on the thermal structure and the thermodynamic structure of the atmosphere, and that's changing if you allow for certain MHD effects, right?
Yes, exactly.
So,
So, for example, think of something like a bright point, right? It's very, very small. So what is happening is you have magnetic fields. It changes the local thermal structure and the geometry. By the way, this is what makes the radiative transfer a beast. The geometry matters. So when you have undulations in the optical surface, so it's not all parts of a let's say hollowed out area is heated and cooled equally. It depends on which direction the rays are coming on, what part is cooling, all of that matters. And so the magnetic fields change the thermal structure, it changes the opacity, which changes the undulations of the surface, it changes the ways in which the rays, propagate. And so this is basically, so the radiative transfer it took just the radiative transfer part basically took 5 years to implement. And so so like you said, so the disentangling part is the funnest and the most difficult part of all these simulations. So what you do is, so you have, the good thing about it is that you can play God. You have all the terms at your disposal. So you try and look at these individual terms and you see how they behave. What does the radiative flux do here? What does the radiative flux do there? And then you try and get a sense of it. And that is really the funnest part.
Okay, any more questions? Okay, if not, then sorry, go ahead. Who's this? You can go ahead.
Yeah, so it's just about the model. So the box which you talked about, so is that are the dimensions fixed, or can it be extended? So what I mainly want to ask is that is it possible to have simulations of multiple sunspots and see?
Yeah, sure. Yes. So actually, that is something that I've tried a lot of things, not all of them work out, but yes, you could have very large boxes, and in that case, you lower the resolution a little bit. You make the things coarse, and you can put in multiple sunspots and see what that means. And I actually have something. I didn't talk about it because it would take forever. But look at this simulation, for example.
Oh right, yeah. I was.
You could have something like this. Yes.
Okay, yeah, that's great. Thanks.
Okay, if we do not have any further questions, and I'm assuming now that there aren't, Mayukh, thank you very much for your talk.
Thanks for having me here.
You're welcome. And remember again that Mayukh could be around and he'll be available to speak to folks from 5:30 to 6:30 regarding careers in Germany. All right. Thank you everybody for joining in, and we can break for a coffee now.